Now, if you haven't heard the term transient before, this refers to the time interval when the output is changing from one steady state behavior to another, in this case, from one constant value to another. We recently introduced the idea of a feedback loop and the feedback interconnection. And in this presentation, we'll talk about feedback control, which is a very common technique in engineering to make machines and processes behave in a good fashion. So what is feedback control? In feedback control, the output is measured and the input is adjusted so as to make the output perform properly. Another name for feedback control is closed loop control. One of the main ideas in feedback control is the idea of an error signal. This is the difference between the desired value of the output and the actual value. So E of t would be y desired of t minus y of t. In block diagram form, this is achieved by a summation junction that takes the difference between y desired of t and y of t. The input signal to the system is then adjusted on the basis of this error signal. Here is the same block diagram that we saw on the previous page. It's just been redrawn. I'm still showing the error signal as the difference between the desired value of the output signal and the actual value of the output signal. Now I show the actual value of the output signal coming from the right. I've done this to make it easier for you to understand the diagram on the following page. This block diagram shows a typical feedback control system. You can see, as in the slide before, that the error signal is created by taking the difference between the desired value of the output and the actual value of the output. This creates E of t. This error signal then goes into the control system. The control system uses the error signal to decide what the input to the system to be controlled is. This input is x of t. X of t is chosen by the control system in order to make the output y of t what we desire it to be. The physical system whose output we are trying to control is referred to as the plant. This is the system which has the input x and the output y. For the continuous fryer system that we talked about in the last lecture, this plant would be the fryer, with input being belt speed, x of t, and output being chip moisture content, y of t. The actual chip moisture content would then be compared to the desired moisture content, which might be, say, 15%. This generates the error signal. If this error signal is positive, this means the chips are overcooked, and if it's negative, it means they're undercooked. So if the error signal was positive, that is, the chips are overcooked, the control system would likely speed up the belt in order for the chips to spend less time in the fryer. On the other hand, if the error signal is negative, indicating the chips are undercooked, then the control system would slow down the belt speed so that the chips would spend more time in the fryer. You see, the control system embodies the logic of how to adjust the signal x of t on the basis of the error signal. Depending upon the application, this control system may be a computer, an electrical circuit, or even a mechanical system. The key aspect here is that it adjusts the signal x of t in response to an error signal, E of t. This sort of control is referred to as feedback control because of the presence of the feedback loop, highlighted here. The control system is often referred to as the controller or the feedback controller. The trick to feedback control is deciding how the input x should be adjusted on the basis of the error signal E. And you can take several courses discussing all sorts of different ways of building control logic. The key difficulty in feedback control is that everything is happening at once. Everything is changing at once. It's not like one variable changes, and then we wait a period, and then another variable changes. Y of t, x of t, and e of t are all simultaneously changing and influencing each other. This can make it difficult to think about how one designs the control system, since everything is interacting with everything else. Let me close this presentation by mentioning that feedback control has additional benefits beyond those we've outlined previously. First, feedback control improves the quickness of system response. We can often make a system's output more quickly move to desired value with feedback control than we can with open loop control. Second, feedback control makes a system less sensitive to variations in the system's components. Third, feedback control allows a system to behave more linearly when there are nonlinear components within it. And finally, feedback control can make unstable systems into stable ones. This benefit cannot be achieved by open loop control.